Okay, hi everyone. I'm Toby Davies from UCL. I'd originally meant to talk about my new agent-based model for fire evacuation, but it was falsified about 5 hours ago. So I've cobbled together this old thing about modelling of crime with a view to prediction and the role of the street network in informing patterns of urban crime and what that means for prediction. So, predicting crime, it's pretty obvious that that's something that we'd like to do. If we can predict crime, then we ought to be able to do something about it, glossing over the question of what exactly we would do about it. But we'd like to know where and when crime is going to happen. But if you try and do that, then if you just plot crimes on a map like that, those are some crimes in London, you just get a pattern that looks pretty much like noise, and you can infer some clustering out of that, but not a great deal more. And it's difficult to see where you would go from there. But predict crime people do. And these are some companies from America who've kind of built on some work that was pioneered in the UK a few years ago, and are now making big money by taking police forces' data and offering to say where and when crimes are going to happen tomorrow. They plot boxes on a grid and say, you should send your cops here, and that appears to be showing quite good results for preventing crime. So, how is that happening, and what can we do about modelling crime as well? So there are two main things that let us get a foothold into modelling crime. The first is the fact that some places simply experience more crime than others. So the red line there is just a Lorenz curve of the cumulative addresses versus the cumulative incidents. If we order the street segments of a big UK city according to how many, I think it's burglaries they experience. I'll mainly talk about burglaries in this talk, but a lot of it, that's just for concreteness really, a lot of it is applicable to a much wider array of crimes. So crime is concentrated in space, and to a certain extent we can say why that is, because it has a relationship with demographic factors and various other things that have been the subjects of criminology for a while. The other thing that lets us do something is the phenomenon of near-repeat victimisation. So this is the idea that when a victimisation occurs somewhere, there's a temporary elevation in the risk that that property, and indeed its neighbours, will be victimised in the immediate future. So this is just a graph that shows a red victimised property, and this is the probability that it'll be re-victimised within 1 week, whereas the orange line is the probability that it'll be victimised 2 weeks later, and the curve just tends to decay like that. So we have this brief elevation in mainly the same offender returning to a place or its neighbours to re-offend against that. And that is present in just about all data sets that have ever been looked at for this kind of thing. And both of those have implications for modelling, and we can do something about those things. So in the first case, that tells us that we can try and work out what it is about certain places that makes them conducive to crime and incorporate that in a model. And in the second case, we have this idea where we can somehow encode this increase in risk and allow it to spread to neighbours and leverage that to see how things like hotspots of crime form. So a lot of modelling effort is focused on ideas like this, where you have crime risk being a combination of static factors and some sort of dynamic thing based on recent activity. And they've been relatively successful in doing that. So models of crime, and burglary in particular, tend to sit on a kind of boundary between agent-based and differential equation-based approaches. So if you look at how these things are specified, often they're specified in kind of agent-based terms. So they talk about offenders walking maybe randomly around a city, sniffing out more attractive opportunities and being biased towards those, burgling them, and then the risk at those places being boosted for a temporary period afterwards. But in a lot of those cases, they're simple enough that they can be summarised by differential equations, and people can do kind of continuous mean field simulations of those things. And they're relatively successful in replicating some stylised facts that we know are persistent about crime. So, for example, the time course of victimisation. This is, again, this repeat victimisation idea. This is an agent-based model from 2011, which shows relatively good agreement with the kind of graph that I showed on the previous slide about how risk decays over time and over space. And we also have models that can produce hotspots as well. So yeah, these are kind of reaction diffusion type continuous models, and we get these hotspots forming with various different morphologies, things like that. But one thing that you'll notice about these figures is that they look a lot like figures from academic papers and not a lot like urban areas. And they're not particularly reflective of what's really happening. This is just a continuous 2D media with nothing much else going on. So our interest is really in incorporating realistic urban form and what that means for models like this, and in particular, the role of the street network in doing this. So why should we be interested in the street network and the effects coming from it? Well, firstly, in the case of something like burglary, for which it's particularly obvious, targets are arranged on the street network. So everything's got an address, that's where the targets are. Also, offenders move around the street network, so that's how they access their targets, and that's how they escape from them, for example. But thirdly, we have this idea where if we just think about risk moving through space, we get counterintuitive ideas about where risk should go. So just to take a playful example, here's just a piece of map that I cut out of Newcastle upon Tyne. And suppose we had a crime happening there. Any crime analyst in the classical British mould would draw a circle around that and say that's where crime's going to spread out. But if you do that, you'll send some police to the sea, and no burglaries happen in the sea, right? But even apart from that flippant example, if we have a crime happening there, say, if we draw a circle around that, then okay, that's more realistic in terms of what the urban area is like. But we have it diffusing over to this street there. So actually, that street, it's close in Euclidean sense to where the incident happened, but it's actually miles away if you actually want to travel there. You've got to go all the way around, literally round the houses to get there. So why should risk communicate over that space? And indeed, it almost certainly doesn't. So to think about some of the theory of why that doesn't, here's a brief introduction to kind of environmental criminology and the theory of why these things matter. So crime pattern theory is a kind of the predominant theory of this kind of thing. And what that states is that if we're thinking about how offenders decide where to commit crimes, they commit crimes in places that they know or that they have awareness of. And the way that they gain awareness is during their daily activities, which may well be of a non-criminal nature. So it might be, so they have certain activity nodes, they're walking around, traveling between these nodes, and as they do that, they form an awareness space, which is the kind of places that they're familiar with and that they might have some idea about the criminal opportunities there. And of course, all of this is down roads. That's how people are moving around. And some of that is going to intersect where there are genuine opportunities for crime. So things where some sort of rational actor will think, yes, I will commit a crime here. So by thinking about where these awareness spaces happen, we can think about where people will tend to be aware of crime and where they will therefore offend. There's kind of this duality between awareness space and kind of criminal intensity. And aggregating this up across multiple offenders, the kind of obvious corollary of that is that places or streets that are in more people's awareness spaces, so that more people travel along habitually, will experience more crime. Okay. So we can easily start to think about analysing networks in these terms and see if we can get some results out of that. So it's trivial to represent a network, a street network as a graph. There are multiple ways to do it, but here I'll talk about what is known as the primal representation, where you simply place nodes at all of the junctions of the graph, so that's anywhere where there's a choice of route, and then connect up any two junctions where there's a street leading from one to the other. So that's just exactly the way that you would naively encode a graph. And what can we measure about things like this? Well, we can measure loads of stuff, but the most immediately obvious thing to think about, particularly given this kind of pattern theory idea, is betweenness. So thanks to Neil for teeing me up nicely by referring to that in his talk a minute ago. I'm going to patronise you slightly more by showing a video of how betweenness builds up on a street network like that. So the idea of betweenness, this may be tedious, but in case anyone doesn't know, the idea is that you take every possible pair of origins and destinations, find the shortest path through the network between those things, and every time a link features, so I'm talking about link betweenness here rather than node betweenness, for those who care. Every time a link features in a trip, you increment its score by 1, and there the reddest link in the graph is the most between, and it's kind of picked out the most central there. There were quite a lot of people yesterday making the very good point that shortest paths aren't necessarily the best way to think about travel in an urban area. That's absolutely true, and I make no bones about that. This is just a first order way to kind of approximate these ideas. So if we draw betweenness for a realistic urban area, this is the city of Birmingham with street segments coloured according to betweenness. You can see on the right that it kind of picks out what you'd intuitively think were the busiest streets. And as a point of interest, this doesn't match up in any way sensibly with the Ordnance Survey classification, so the official classification of these roads. You get roads which are called major roads, and there's a huge variation in how you would estimate those to be used across their length, partly because they are very long and a classification applies to an entire road rather than a street segment. So, does this have a relationship with crime? As much as there's a perverse appeal in setting up results which turn out not to exist, I wouldn't have brought you here if there wasn't something in this. So, this is looking at police calls for service in Camden. That is exactly what it says on the tin. It's where the police are dispatched according to 999 calls. And one method which was proposed for kind of looking at urban activity versus street network properties was following this paper by Porter et al., where the idea is simply to compute KDE surfaces of these two things and then look at the correlation between the two. So on the right is the KDE surface of betweenness, on the left it's the calls for service. The blotchy artifact is because of the nature of the data, and we have kind of done some work on re-scrambling that. Anyway. You can kind of identify some points of interest where it looks like there might be something in this. And indeed, when we do the correlation, these are relatively good, I would say, and they certainly tally up quite nicely with what's shown by this approach in the other context, which is of economic activity in cities, in the case of Bologna and Barcelona. So these are showing that betweenness is, in this case, quite a good predictor of these activities. On the other hand, we can look specifically at the street segments. So take street segments as the unit of analysis. And in this case, this is taking all street segments of Birmingham, ordering them in increasing order of betweenness, and taking a moving average of burglary rate as we move through those. And there's a reasonably pleasing trend through that, where it's around about 40% more crime is happening at the more between end of the spectrum than at the lower end. And that all stands up with very large significance if you run proper statistical models on that as well. So it looks like there's something in this betweenness, and we'd like to encode that into a model on a network as well. So how do we do that? Well, the obvious approach, given all I've said about people building up activity spaces, offenders making decisions about how they move around, it's kind of obvious that you might want to think about an agent-based approach in this case. But I would argue that you don't really need to do that, because for the purposes of what we're talking about on the time scale of single incidents and how the risk from a single incident might evolve, not much of what an agent-based model might tell you actually changes. So thinking of the two components that we have in our model, the underlying risk side, if we're saying that pretty much that at least partially corresponds to the level of use of streets, that doesn't change in response to a burglary incident. People still obey the same habits, people still generally go where they used to, and offenders still pretty much know where they are. In the case of risk diffusion, that actually doesn't change either, because from the point of view of someone who's modelling this, we see an incident happening, but we don't really know who has committed that, and we therefore have to think in general terms. So the question of interest is therefore, if a general offender that we know nothing about other than that they offended on this street is going to offend again, which other places might they know about? And again, that's something that we can pre-compute. We don't need an agent-based model running live to know about that. You could kind of argue, I guess, that betweenness is like an extremely primitive agent-based model, but still, debate that for yourself. So the way that we do it is just to simply run one differential equation for every street segment, representing the dynamic risk. So this is the risk according to this near repeat effect. If effects changing over short timescales, like 1 week, 2 weeks. And this is what it looks like, and this is what everything is doing. So in the first part of it is talking about boosting effects due to offences that have recently happened. And offences are happening at a rate which is the sum of the static rate. We're saying that that's a function of kind of street network properties and how busy certain places are. Obviously plenty of other things as well, but for the purposes of this, just that. And the dynamic rate that's going on in our model. We also have it simply decaying over time. These effects don't last forever, they go away. And we also have it diffusing from segment to segment. Simply in this case from each segment to its neighbouring segments, though there's scope for making that more complicated. So if we do that, that network that I constructed earlier from Liverpool, here's what it looks like when you strip away all the redundant background. First thing that we can do is kind of take away this endogenous boosting feedback mechanism and just initialize it with a spike, which might represent a burglary just in a very simple way, just to see what kind of effect this has. So if we do that on the left, it diffuses out pretty much as you'd expect to its near neighbours, saying that the risk has gone up on those. In example 2, it diffuses out, but slightly more widely. And the reason I chose those two examples is because E1 and E2 in my diagram are two segments which are very close and which in traditional crime modelling, you'd have risk diffusing from one to the other. They're very, very near in spatial terms. But they're actually a long way away, or a relatively long way away, in travel terms. So this is demonstrating in a very trivial way that it doesn't just diffuse from one to the other. If we feed in some stochasticity in this so that events are happening randomly according to these rates that we've encoded. This is a well speeded up version of what might happen, but you see some kind of hotspots coming up. Here's an area here which is being repeatedly victimized due to kind of feedback effects. There's one down there as well that I'll soon fall behind if I try to chase them around, but that's generally what it looks like. We can also look at put the whole thing back together and look at how this goes to an equilibrium, which it does under most sensible conditions. So if we encode this with what I've kind of been leading to, which is saying that the static rate is proportional to betweenness, that's what betweenness looks like on the left. And if I run the model, it will converge to an equilibrium which looks kind of like betweenness, but not exactly like betweenness. So there's some redness happening, for example, on here, that we don't see in the betweenness thing. The colour scales match exactly, by the way, and generally it's a lot smoother in this case. And I certainly won't go into this, but you can find quite a nice link between the spectra of the street network and its Laplacian, and why these patterns flatten out as they do. And there's a bridge from that to looking at kind of community structure in street networks as well, and why certain sort of insular structures will have will tend to insulate crime, and why they're not leaky in a criminal sense. We can also look at kind of model interventions that the police might want to think about implementing in something like this. So if we artificially crush the crime on the this is what the equilibrium previously looked like. If we artificially crush the crime on here, then not only do we turn that right down to zero, but we get a diffusion of benefit, which is what the police really like. By just policing that, we get flattening out in the local area, and overall crime goes down. And a similar idea is removing a link. Now that's certainly an excessive intervention, but instead of thinking of shutting a road, you could think of it never having been built in the first place, if we want to think about, say, how this might inform planning. So if we remove that, we get a similar kind of effect. This is taking a bit longer than I'd like it to have done, but that will settle down as traffic is rerouted around the rest of the network. A route like this will become more important, and crime will go there. But you get some quite unexpected non-linear movement in this, where crime kind of moves to unexpected areas when you do an intervention like that. So that's the kind of thing that we could look at with that. And just as a hint of where we've taken this, which I haven't talked about today, but where we're looking to take it now, one of the big questions is the question of directionality. So I've said that crime preferentially happens on these things, but at the moment I've just had it radially diffusing out to neighbouring segments. It looks like it doesn't actually diffuse uniformly in all directions, and actually in a quantifiable way you can say that the crime is more likely to diffuse down a certain road than down another road, in a way that kind of corresponds to betweenness-like ideas. So you can kind of say that if E2 is targeted here, then crime is more likely to diffuse down this kind of main route than down these, which are kind of more redundant street segments. And that seems to hold up statistically. The other obvious things to look at are calibrating this and deploying it on real police systems, which is the next step, and the inclusion of policing, which is a big unanswered question. No one really knows what the effect of policing is when you put it into a model like this. And that feeds me nicely into a plug for the project that I'm part of, which is looking at precisely that question. So this is a collaboration between UCL and the Met Police, where we have access to, or soon will have access to, a large set of police movement data, where we're hoping to quantify the effect of, say, police patrolling or visible policing on crime patterns. And
thank you.